The whys and wherefores.
In road traffic, we need to be alert and to react swiftly, just as we do in playing games. Sometimes we react quickly and correctly, and another time we react much too slowly and wrongly. Why is this? We need to be particularly alert if we're driving, because we're moving much faster than we do on foot. Balancing calls for swift reactions, and so does grasping a falling stick, as Janet demonstrates here. She doesn't react at once, though. Obviously, it always takes a little time.
The reason is clear. The brain is the centre from which commands are passed to various parts of the body. Commands like, open your eyes, lift your arm. This information is transmitted from the brain by nerves. The greater the distance from the brain, the longer the reaction takes.
This is why George takes some time after he sees the stick falling to close his hand. Still, not a bad attempt. We don't always react at the same speed. It depends, for instance, on whether we're wide awake or sleepy. For motorists, it's important to be wide awake at all times. Reactions can be tested on this simulator. By means of a lever, the car is kept on the twisty road. Every contact counts as a minus point. George is doing quite well. He's steering the car along the road with only a few mistakes. After a time, his mistakes get more frequent. He's tired, his concentration is deteriorating, his reactions are slowing down. But in other respects, too, our bodies don't always react in the same way. Take the eyes, for instance. We can believe our eyes, or can we? Here we see slanting lines, which aren't parallel. Or are they? The rule is straight. If we use it to compare the slanting lines, we find that in fact they are parallel. Our eyes are misled by the short lines. So, can we always believe our eyes? Here's a photo of a mountain. Now the mountain's turned into a crater, and then it's a mountain again. Our eyes deceive us because we interpret the shadow on the left of the picture as a sun shadow. These figures are the same size. Here's the proof. Now the figure in front looks bigger than the one behind. If we reverse the figures, it's the other way round. The converging lines give the impression of perspective. That's the reason for this illusion. Janet is testing to see how sensitive George is. His fingertips are obviously more sensitive than the backs of his hands. And why?
Nerves transmit to the brain what we feel when we touch. Many nerves lead to the fingertips, which is why the fingertips are particularly sensitive.
Another test to show how sensitive the fingertips are. George is blindfolded and Janet pricks his fingertip with 2 wooden sticks. George has to say how many and gets it right. 2. Now the same thing on his neck. George can only feel 1 point because there aren't so many nerve endings in the neck. Here's a way of playing a trick on the nerves. If the fingers are crossed, the pressure is felt in the index finger, although it isn't even being touched. It's really rather odd, this sense of touch.